All righty. Over here. How's everybody doing? So what we're gonna do today is your Cutnell and Johnson. That's gonna be chapter 6, which is gonna be your work and energy. So let's go ahead and start by defining the work. Well, your work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance through the object through which that force acts on that object. So let's go ahead and write it down. So your work equals, again, it's a force acting on an object, the magnitude of the force multiplied by the distance through the object's action upon. So it's your force multiplied by your distance. And let's go ahead and label these. So your F dash your force, your W dash your work. Actually, I don't work better than that. That's better. And D dash your distance. Or the displacement. So now what is your force? Your force is going to be equal to your mass times the acceleration. That means that your work is going to equal to mass times acceleration times your distance. Let me go and label this. This is your mass. Label this as your acceleration. That's why it's important to take a vacation if you're doing too much work. If you have a job and you're doing work, it's too much to take vacation because too much work makes you mad. Mass times acceleration times your distance. Now, in thinking of terms of units, your mass is going to be in kilograms. Your acceleration would be in meters per second squared, where your distance is going to be in meters. Having all three of them, adding them up, what you're going to get? You're going to get kilograms, meters per second squared times the other meter, which is going to equal to your kilogram meter squared per second squared. And we define that as your joule, which is, we give it a big letter J, which is going to be the unit for, actually write it down, the unit for work, which is this little fella right over there. Now, when you have work done against gravity, which gravity is, we give it a little g, and its acceleration, which is going to be 9.8 meters per second squared. And why is it meters per second squared? Because it's acceleration. So your work, which was equals your MAD, is going to become, which is your force times your distance. So this is going to be, you work against your acceleration, is going to be your mass times your gravity times your height. This is your gravity. This is your mass. This little fellow over here. Let me go and label this as your acceleration and this as your distance, which is this little fellow over here. And let's label this little fella as your force. Make sure that you better. All right. So your work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance through which is object force on. And we just saw that the work equals your force, your applied force times your distance, which the force acts on, which is your force equals to mass times acceleration. So your work makes you mad. The work done against the gravity, your acceleration is going to be the gravity. So, and your distance is going to be the height, so it'll be mgh. And again, doing that, we just derive a joule as a kilogram meter square per second square, where that's the unit of work, which is named after James Prescott Joule, which he died in 1889. He had a little experiment. So in his experiment, go ahead over here. He got a Joule's experiment. Let me just write this down. Joule's experiment. So he got a paddle of water, a little container that had water into it. And in there, he had a pedal. So let's say this is over here. Our pedal is over here. And outside the pedal, I guess that's a pulley, if you want to. And in here, he has a weight. And those little things. It's a paddle, or you could say it's a paddle wheel. And he put a thermometer. And so let me just go ahead and draw a thermometer. So he had a small paddle wheel inside a container of water. And when he put the weight on there, the paddle started going faster. The faster the paddle is going, the temperature, the temperature goes up. So the friction of the heat of water, the same amount of water always produce the same amount of the heating. And that's your Joule's experiment. And here's your little pedal of water, it's a better picture. And when the pedal is going, the faster they go, there's that in the thermometer, there's a rise and the temperature. That brings us to defining a power. Now, we first start defining the distance, which was, let's say your delta x is your change in position, which is your final position minus your initial position. Define the distance by your time, which is v over t, and what you get, your velocity, which we give it letter v. Define the velocity by your time, which is v over t, and what you're gonna get, you're gonna get your, as delta v over t, is you're gonna get your acceleration. Multiply that acceleration, which is letter a, times mass, which is basically ma, and you're gonna get your force. You're gonna multiply that force times your distance, which is your FD, and that's what you get your work. Now, in order to do work, what do you need? You need power. And that's where we define the power at. You get the work divided by time, so your W over T, and that's going to equal to your power, and we're going to give it lower P. So your power is the rate of doing work, and your power is going to equal to your work divided by your time. Actually, let me get it right up here. P instead of a row for power. Now, your work in terms of units that's going to be, we define that as joules. We define the time as seconds. So this is going to equal to your joules per second, and we call the joules per second, you get a different color over here. We call that a watt. And we give it the letter W for your unit, and that's going to be your unit for your power. So the power is the energy, is the rate of doing work. Awesome. Now let's define energy. Now, your energy is a property, something enabled to do work. Is the property that enables us to do work. Now, there's going to be two types of energy we're going to be talking about. The first one is going to be your kinetic energy. And your second one is your potential energy. Now we're going to get for that kinetic energy, KE, potential energy, PE. So let's go talk about this for a second. Let's go talk about kinetic energy. Just make this a little. All right, so kinetic, write it down, energy. Which is the energy of a moving object. So the energy of a moving object is called kinetic energy. We define velocity as you're going from one point to another over a certain amount of time. It's your distance over your time. In order to achieve that, you need energy. You're not gonna have a velocity without energy. Now, your kinetic energy is defined as mv squared over r, where your m is your mass in kilograms, your v, that's your velocity, and it's meters per second, and r, that's your it's 1/2 mv squared. So it's over 2 over r. Your mass is kilograms and your velocity is meter per second. Adding those up, what you're going to have kilograms meter squared per second squared. And again, that's going to be your joule, which is going to be your unit for kinetic energy. So your kinetic energy unit is always joule. Again, it's energy, so it has to be in joules. Your kinetic energy is going to be mv squared over 2, which is going to be kilogram meter squared per second squared. So let's go back over here. So what is the kinetic energy of a 1,000 kilogram car whose speed is 10 meters per second? So let's do this example over here, shall we? this example is telling us that your mass is 1,000 kilograms and your velocity is 10 meters per second, and you need to find your kinetic energy. Where your kinetic energy again is 1/2 mv squared, or I like to say the mv squared over 2. Both ways correct, which is going to be your 1,000 times 10 squared, that's 100, divided by 2. So what you got? You got 1, 2, 3, 4, 5, 100,000 divided by 2, so that's 50,000 joules. That's how much your kinetic energy will equal to. All right, that's the first one about kinetic energy. Now let's talk about potential energy. And potential energy, it's like you said, it's potential. When somebody says you have potential, what do they mean? It means you have the ability to do something, but you have not done it. Same thing with the potential. Potential energy is stored energy. Given the right circumstances, has the potential to do something. Now, for examples, you have your gravitational, for instance, your spring, your electromagnetic, etc. That's all on your potential energy. Now, your gravitational potential energy is the work done by the gravity, which is going to equal to your mgh. Again, h is the height, g, that's your gravity, which is 9.8 meters per second squared, and m, that's your mass. Now, energy can be transferred from one form to another. It can go from kinetic to potential, or potential to kinetic, etc. Potential to work. So let's go ahead and watch these little videos that we have right now. All right, so here's the first movie we're gonna watch. So in the first one, we got a ball of mass m, whatever the mass is. It's pushing on with a force v that's creating a velocity v. Notice, because the work equals your mass times acceleration times your distance, notice the work that's going up. The more you go, the longer it is, the more work you have. And it's over here, you can see how the work goes on. Now, what if we double the amount of force? So let's say in the second video, we double the amount of force. Notice that the work is actually doubling. So the more work you have, the more force you have, which is this little arrow over here, the more work you're gonna generate. All right, now let's go ahead and watch this video. So this pile driver is showing the energy, how you can do it when you raise it with work. The higher it is, the more energy it is to drive the nail in. This is a high at 70 centimeters, dropping down to the nail. Is the double weight driver at 70 centimeters with double the weight, which means you're gonna have work equals mass times distance. That means in the kinetic energy is mv squared. You have more mass, that means you have more kinetic energy. That means the greater the fall on that driver. Here is an arrangement called an energy. Now here's our energy wall. If you put a ball, it will roll back and forth. The question is how much higher than the low side that we need to release the ball in order for it to go over the hump. Here's your low side over here. So I was thinking this is the low side over here. Would it be below or at the same or a little higher or so much higher? What do you think? All right, let's take a look at the other video. So you need a release point only slightly higher than the low side to release the ball. The reason for that being is you give it just enough energy to overcome the hump. If you do it the same side, it will have enough energy to go on the hump, but it will go down because it will not have enough energy to go over the hump over here. So you have to put it a little bit over the low side. Now each track is different steep. So each one has a different slope. So he's going to release the ball from the track. How high will it rise on the other side of the slope? Will it go on the steepest, the middle one, or the least steep as the highest point? What do you think? Here's the ball. So when he released the ball in each one, the ball rises the same height to each one of them. The reason for that being is when he released the ball from over here, it had enough energy to go the same distance on all of them. So it's the same energy, so they all rise at the same height on each one of them. Now, the best example when we talk about kinetic energy, potential energy is the pendulum. When you have a pendulum, it rotates between kinetic and potential energy. So when it is on the top, as you notice over here, your potential energy is the most, kinetic energy is the lowest. Going down, your kinetic energy increases, your potential energy decreases up until a certain point where your kinetic energy is the maximum, potential energy is the minimum, and then potential energy takes up until your kinetic energy goes down to minimum, and it keeps on back and forth going on the same way. And that's what you talk about is transformation, or or the law conservation of energy. Energy cannot be created, destroyed, but it can be transformed from one form to another. So again, when you talk about a pendulum, let me go ahead. You're talking about, let me go talking about a pendulum. Go ahead. You're talking about here's the ball over here, it becomes over there, and it becomes right over here. Over here, your kinetic energy is lowest, potential energy is highest. Same thing at this point. Your kinetic energy is your lowest, your potential energy is your highest. At this point, your kinetic energy is your highest, and your potential energy is the lowest. Now notice it is transforming between potential and kinetic energy. So your energy is transforming from one form to another. Now, talking about energy, let's talk about this last video over here. If we release a ball in front directly from a person's face, would it smash his face or not? What do you think? Let's take a look. The ball is released and barely misses. The reason is that the ball comes back to where it belongs, because that's the most energy goes up and down in. So it's not going to go higher because it didn't have enough energy. Now, if he started the ball off beyond his nose, then yes, his face will get smushed. Now, so your work is defined. So we define the work as your force times your distance. Now, let's say you're going at an angle though. So let's say, I don't know, this is you right over here, and you are taking a trip. So you got a suitcase that you're actually dragging, and it has wheels on the bottom, and you're actually taking it this way. Now, when you're moving, you're going in, you're moving that way. Your force is acting on here. So let's just take this and let's just draw it over here. So you got your force going in there. And then we learned from before that this force is going to be resultant from your F in the Y direction and F in the X direction. And this is actually defined as your F sine theta, F cosine theta. Now, you are moving in the X direction. That means we are moving towards the F of X. So that means that the work done is going to be equal to your Fx times the distance d, which is your F cosine theta. This is your angle theta, which again, this is, let's say this is the wall. This is your angle theta over here. Times your distance d. Now, if theta, let me go ahead and pull this up a little bit so I can have a little room to write. Now, if theta was 0 degrees, that means all right. So if we say that theta was 0 degrees, that means, let's say call W1, our work is going to equal to your FD cosine theta. Let me actually rewrite this down as FD cosine theta. Just easier to write. FD cosine theta, which is going to be FD cosine 0, which is going to equal to 1. So it's going to be equal to force times your distance. That's why if your angle is 0, your work is going to equal to your work is going to equal to force times your distance. If, let's say you call this W2, let's say your angle this time, let's say your angle is 180 degrees at this time. That means your work is going to equal to your FD cosine theta, which is going to be your FD times cosine 180. Cosine 180, that's going to equal to -1. So it's going to equal minus FD, which from these two, if your total work, which is going to be your work 1 plus your work 2, which is going to be your FD minus FD, which is going to equal to 0. And this is exactly what we have over here. So let's say we have an example of a force being 45 newtons at a 50 degree and a 75-meter displacement. So do this example. Your force is 45 newtons, your theta is 50 degrees, and your distance is 75 meters. And you want to find your work. Again, your work is going to be FD cosine theta, which is going to be 45 times 75 times cosine 50. Plugging this in. Again, you get 2,170 joules. Awesome. All right, going back to our work, which we defined as your mass times acceleration times your distance. Too much work makes you mad. Let me go and label these. Mass in kilograms. Acceleration in meters per second square. And your distance. Where we just defined that, and I'm going to write it down, where we define the work as FD cosine theta, and we do it on 0. So let's say this is 1, so it's going to be equal to FD, where F is your mass times acceleration. Now, from Newton's, from our kinematic equation, let me get a green color over here. Your final velocity square is going to equal your initial velocity square plus 2AD. That means solving this for AD, what you're going to have? You're going to have final velocity square minus your initial velocity square divided by 2. Let me go ahead and label these as initial velocity. And I'm going to label this as your final velocity. Okay, well, what a coincidence. So over here, we have an AD, and over there, we develop what AD is. So we can actually take this one and plug it back in there. So this would mean that the network, let me just say, the network is going to equal to your mass that we had times V squared dS squared over 2 minus V initial square over 2, which is going to equal to your mass times V final square over 2 minus mass times V initial square over 2, where this is going to be defined. Oh, mv squared over 2. Remember we said the kinetic energy was mv squared over 2, so we can define this as kinetic energy final, and we can define this little fella as your kinetic energy initial. That means your work is your kinetic energy final minus your kinetic energy initial, which is going to be your change in your kinetic energy. So over here, we developed the kinetic energy equation along with the work. Okay, let's do another question. So let's say a truck is accelerating at a rate of 1.5 meters per second square. The mass of the crate is 120 kilograms. And the distance down to 65 meters. What is the total work? So let's go ahead and write down the information for this question. This is going to be example 3. We said the acceleration was 1.5 meters per second square. Your mass is 120 kilograms, and your distance is 65 meters. And you're looking for your work. And again, your work is FD cosine theta. We're going in the x-axis. The thing is going to go to 1, so it'll be force times your distance, which is going to be your mass times the pressure times your distance. So in this case, it'd be 1.5 times your 120 times your 65. And what'd you get? Be 180 times 65, and you should get 1.2 times 10 to the 4 joules. So your work is going to equal 1.2 times 10 to the 4th joule. Let's make sure of our answer. And our answer is correct. So the work is the energy transferred by the force. The energy is the ability to do work, And your work is your force times distance, which is your math. Now consider a constant net external force acting on an object. The object is displaced at a distance d, the same direction as the net force. So it's all the forces in that direction times your distance, which is your mass times acceleration multiplied by your distance. And that's what we just saw, where you took that your acceleration, your distance, and from the kinetic equation, Vf squared equals V initial squared plus 2AD, you solved it for your acceleration times your distance, right over here, and you get 1/2 Vf squared minus V naught squared. Plugging in the mass times plugging in the mass, that's what we multiplied by. You get 1/2 Vf squared minus 1/2 V naught squared, which is going to be your initial minus your final kinetic energy. And that's what getting us to the work energy theorem. When a net external force does work on an object, the kinetic energy of the object changes by the amount of the work done on it, which is your change in your kinetic energy. So let's say we have a question. You got the mass of the space probe is 474 kilograms, initial velocity is 275. If you have 56 Newton meter force acted on the probe through the displacement of 2.42 times 10 to the 9th, what is the final speed? So let's go ahead and write down the information from that example. This is going to be example 4. Your mass was 474 kilograms. Your VI equals 275 meters per second. Your force is 5.6. Times 10 negative 2 newtons. And the distance is 2.42 times 10 to the 9th meter. And you need to find your final velocity. Wonderful. Now, your work, which is your FD cosine theta. And we're going to say this cosine theta is going to be 1. So it's going to be your force times your distance, which is going to equal to your change in kinetic energy, which is going to equal kinetic energy final minus your kinetic energy initial. That means your force times your distance is going to equal to your mass times V final square over 2 minus your mass times V initial square over 2. We're solving for the final velocity. Let me go ahead and plug in the numbers over here. 5.6 times 10 to the negative 2 times your distance, 2.42 times 10 to the 9th is going to equal to your 474 times your final velocity that we're looking for square divided by 2 minus your 474 times your initial velocity that we have is 275 squared divided by 2. Solving for this, our final velocity is going to equal to, plug in these numbers in, 805 meters per second. Let me go ahead and check out my answer. Oh, we got 805 meters per second. Now, supposedly you get like a basketball. Let's say you got this basketball right now coming down right over here. So here's your basketball. And you drop it down to the floor. So it becomes right over here. And here's the floor. Now, what is this distance called? Let's say from over here, over here. This is going to be your H naught, where by the way, you got the ball has your weight on it. Weight, which is going to be mass times gravity, which is also affecting over here. Same thing, weight equals mass times gravity. And we can define this distance that it goes in from over here to H final. So your work done in this case was F cosine theta, say theta, let's say cosine theta is 1. So there's going to be your FD, which is your mass times your gravity, because it's going to be gravitational force times your distance. Your distance is going to be your final minus your, your initial minus your final. In this case. So your work in this case is going to be mg h initial minus mg h final. And that's again what brings us to the definition of potential energy. So mghi, we define the potential. You grab it. Let me just write this down actually in a different color so it won't clash with this one. Your gravitational potential energy, we define it as mgh. Your mass times your gravity, which is 9.8 meters per second square, times h, your height. So which makes this your initial potential energy, and it makes this your final potential energy. So let's do another question, shall we? So let's say we have a girl in the swing, and she is swinging 2.2 meters above the ground and 1 meter, 2 meter at her maximum and 1.1 meter above the ground at her lowest, at her minimum. What is the girl's maximum speed? So in this case, we have two heights. And this is going to be just an example swing. So your H final is going to be your 2.2 meters. Your H initial is going to be your 1 meter. That means your distance, your displacement is going to be your 1.2, your 2.2, I mean, minus 1.2, and you should get to 1.2 meters. And we're looking for your velocity. Now, having a girl in the swing, so let's say this is the swing over here. And let's say the girl is right on it, sitting on the swing. The swing is like a pendulum, so it's going to go back and forth. Right over here where the girl is on. She's going to be over here, and then she's sitting right down over there. So it's going back and forth. Let's say this is the floor. So if this was 2.2, this is going to be your 1 meter. You're looking for your velocity. Now, again, you're going from kinetic to potential energy. So your kinetic energy is going to equal to your potential energy, which kinetic energy is going to be mv squared over 2, which is going to equal to potential energy gravitational mgh. Luckily, we have both masses over there in the same mass, so the masses cancel out, which means v squared over 2 equals gh, which means that v is going to equal the square root of 2 times g times h, which is your 4.8 meters per second. All right, let's do another question. Perfect. So you got a gymnast that leaves the trampoline, initial height of 1.2 meters, reaches maximum height 4.8 meters before falling back down. What was the initial speed of the gymnast? All right, let's go ahead and solve this. So this is going to be example 7 in our notes. So your initial height is 1.2 meters and your final height is 4.8 meters. Your we're looking at your final velocity. You're gonna stop, so it's gonna be 0 meters per second. We're looking for your initial velocity. And again, your work is going to be your change between your potential energy and your change. Let me actually put the change in because you're getting initial value. Your change in potential energy, which is going to equal your change in kinetic energy. Having do that means having take these two fellas over here, and again using potential energy, gravitational energy as mgh, and kinetic energy as mv squared over 2. That would add it up to your mass, which is going to be the same. It's not going to be different. Gravity is not going to be different. Initial is going to be initial height minus mass. Gravity times final height is going to equal your kinetic energy final minus your kinetic energy initial. Having take mass times gravity together, what you get? HI minus HF, which is going to equal to your mass final velocity square over 2 minus your mass initial velocity square over 2. But we defined that initial final velocity, the final velocity is 0. So this thing is going to go to 0. And that means your mg times hi minus hf is going to equal to minus mvi squared over 2. And again, your masses can cancel out at this point. Which means that your initial velocity is going to equal to 2 times g times the difference hi minus hf square root. And when you do a square root, always try to close it. That way you know when the square root ends. And having with this one, you would get 2 times 9.8. Actually, forget the negative. Negative 2 times 9.8 times the initial of the height, which is the difference in these two would be delta H is going to equal to 3.6. And it's going to be initial minus final, so it'll be minus 3.6. Your negatives goes away together, and you should get 8.4 meters per second. Let's go check our answer. And we get 8.4 meters per second. So our answer is correct. All right. So let's go back. So in order to transfer energy to an object, you have to extend a force on that object. Where your work equals your FD cosine theta, and F is your force, and your D is your distance or displacement, while force on it now your work is the amount of joules of energy given an object or system. Now your work is going to be positive if the force is giving energy, and your work is going to be negative if the work is taking energy. Your network is going to equal to first work plus whatever second work plus whatever third work plus etc., which is your net force times your distance. Now, there's two types of work we're going to be talking about forces. The first one is your conservative force, which is your work done by a force depends on the initial and final position. So work done by a force depends on initial and final position. For instance, let's say we have an object that is 5 kilograms. Kind of like, let's say, a elevator that weighs, a small elevator that weighs 5 kilograms and is going down an object of 6 meters. Now, this is going to have a weight, which is mass times your gravity. So your weight, which is actually a force, which is mass times acceleration, which acceleration is going to be mass times gravity, which is going to be 5 times 9.8 in this case, which is going to be your 49 newtons. That means the work done is going to equal to that force times your distance, which is your 49, times your 6, which is going to be 290 newtons. Now let's go. Let me go ahead and get this. Now, let's take this object that we have. Let's say you got the first one, you go down 6 meters. And then that elevator goes back up on the second try for 6 meters. On the third one, it goes back down at 6 meters. Notice that this one opposes gravity. Now, if you calculate the work on situation number 1, your work we just calculated is going to be 294 joules. In situation number 2, your work is going to be opposite gravity, so it'll be minus 9.8, so it'll be minus 294 joules. In situation number 3, your work is 294 joules. So your force is conservative. So the work done by the force depends on the initial and the final position of that object. Wonderful. And that's what we talk about. Let's say you have a roller. I don't know. I like going Six Flags. So let's say you got a roller coaster that's going in this way, and let's say you got 8 cars. Let's say this is our cars for the roller coaster. Roller coaster is the best example because with the work done by gravity, WG is going to equal to mg H initial minus H final, which means that your H initial is going to equal to your H final. For your work. So because you're starting off and you're coming back in the same point, your work is going to equal to 0. So when this equals to 0, so 0 over mg is going to equal to 0, is going to equal to hi minus hf. That's why your initial is going to equal to your final. So you can non-conservative work do not conserve mechanical energy. Conservative work conserve mechanical energy. So conservative is from their name. They conserve mechanical energy. Your non-conservative work, such as static and creative, let me go ahead. When you talk about non-conservative force, we're talking about your static and kinetic friction. Your tension, your normal force, etc. All of these do not conserve mechanical energy. And what's the mechanical energy? We define the mechanical energy as the sum of all mechanical energy in the system, which is your potential energies plus all your kinetic energies. You see, if you got an object, let's say we got an object, let's say a block right over here. And let's say you move the block back and forth, right? So if you move the block one way, you're going to have your friction going opposite. And, you know, same force. Let me go ahead and do this. So if you keep going back and forth, what's going to happen? Well, if you do that, it's going to get hotter. That means the thermal energy will go larger and larger. So the work done by friction depends on the path taken. So friction is not a conservative force. you're not going to conserve the energy. The energy is going to be wasted as heat. So when you talk about conservative, and non-conservative, if you have a gravitational force, the potential energy gravitational. A spring force, for instance, you get a spring potential energy. For non-conservative, if you have a friction force, you do not have a potential energy friction. So with friction, there's no potential energy associated with it. See, in normal circumstances, your network is all your conservative forces and all your all your conservative work and all your non-conservative work. So this is conservative work, non-conservative work. And again, so your work done, I'm just going to say it's just a work done. Except in the force is your final kinetic energy minus kinetic energy initial, which is delta KE. Your conservative is going to be your gravitational work, which is your MGHI minus MGHF, which is your potential energy initial minus potential energy final, which is your minus your change in potential energy. And that's what we just saw. So plugging that in, where your work equals your conservative work plus your non-conservative work, that means your delta KE, which we just defined, is going to equal to minus the change in potential energy plus your non-conservative work. That means your non-conservative work is going to equal to all your kinetic energy plus your potential energy that we have, which is going to equal to your kinetic energy final minus your kinetic energy initial plus your potential energy final minus your potential energy initial, non-conservative. Let's just organize this with the final and initial, which is what you're going to have. You're going to have, let me actually make this a little larger. You know what? Let me get a different color so I can, right? So that means is going to equal your kinetic energy final plus your potential energy final minus your kinetic energy initial minus potential energy initial, which this is defined as your final energy and this is defined as your initial energy. So from these two, your non-conservative work is going to equal your final energy minus your initial energy. If the network equal to 0, so WNC is going to equal your final minus your energy initial. If this goes to 0, that means your final energy is going to equal to your initial energy. And that brings us to the law of conservation of energy. Your energy before is going to equal to your energy after. So that means your total mechanical energy is E, which is going to be your all your potential plus all your kinetic added up together. So your non-conservative, which is your final minus your initial, which is going to equal to your potential energy final plus your kinetic energy final minus your potential energy initial plus your kinetic energy initial. And in this case, it will equal to mghf plus mv squared over 2 final minus mghi minus mv I squared over 2 initial velocity. All right. So let's do this. Let's do this one example, example number 8. Notice I'm deciding to leap across the canyon by driving horizontal up the cliff at 8 meters per second. You know the resistance. Find the speed of which the cycle strikes the ground on the other side. And so let's go ahead and write down the information for this question. It's going to be example 8. So our initial speed was 30, how much was it? 38 meters per second. And we define the heights as 70 and 35. So HI is 70 meters, HF is 35 meters. From these two, delta H is going to equal to 70 minus 35, which is 35 meters. And so you get the V, you get the H's, and what you're looking for? You're looking for the speed, final speed. Now, using the equation that we developed, your energy before, mechanical energy before, is going to equal your mechanical energy after, or let's say final equals initial, or initial equals final. Doesn't really matter. They're both interchangeable. So this one be m v final squared over 2 plus your mg h final is going to equal to m v initial squared over 2 plus mg h initial. Solving, so your masses cancel out, which is nice. And then solving for your final velocity, this is going to equal to your square root of, so this is going to move over here. What you're going to have 2 times G times the difference HI minus HF plus VI squared, which is in this case is going to be square root of 2 times 9.8 times our 35 that we found, plus your 38 squared, which means that the V, let me actually write this down in different colors, so one clash, your V final is going to equal to 46 meters per second. And that's exactly what we just got, 46.2 meters per second. All right, now let's do one last example, shall we? Go ahead over here, new slide, get 2 new slides. Okay, this last example of this chapter. Assuming that 0.2 kilogram non-conservative force generated by a burning pellet does 425 kilojoules of work. What is the final speed of the rocket, ignoring air resistance? So let's go ahead and write down the information for that question. And this is going to be example 11, our last example of the chapter. So your mass is 0.2 kilograms. And so your H final is 9.8. How much is the H final? 29 meters. 29 meters. That means your initial was at 0 meters. That means your delta H in this case is 29 meters. And your work is 425 joules. Let me actually write down the work better than that. And you're not trying to find the final velocity. And again, your non-conservative work, let me go ahead and write this down. Is gonna be your delta PE plus your delta KE, your all potential plus all your kinetic, which your potential is going to be mg, same mass, same gravity, final height, minus mg initial height, plus mv final square over 2, minus mv initial square over 2. That means our non-conservative work is going to equal to now we said that your final velocity is 0. We didn't define the initial velocity, which is going to be 0 meters per second because you were starting off. So this means this thing is going to go to 0. So your non-conservative work is going to equal to mg times your difference in the heights plus mv final square over 2, which is going to equal to 425 joules. So 425 is going to equal to your 0.2 times 9.8 times your difference, which is going to be your 29 meters that we got, plus 0.2 times your final velocity square over 2 that we need to find. Solving this to the final velocity square. It'll be 425 minus 56.84 times 2 divided by 0.2. And this is going to be square, so don't forget the square rooted. And I got square root of 3681, which is going to equal to 60.6, I'll say 61 meters per second. I'm just going to approximate. And let's check. And that's our answer. And that should conclude chapter 6. I hope you enjoyed it. If you have any questions, just go ahead and give me a call, or you can email me at abunaemeh@gmail.com or 256-348-1480. This is Malek Abunaemeh. Thank you so much for watching. I do appreciate it.